Welcome to this tutorial about significance testing in an SEM model. If you run a structural equation model, you have different options how to test the significance of a path coefficient. You can use the z-test, which you get in the standard output, or you could use a likelihood ratio test or chi-square difference test. And in this video I'll show you why the z-test is highly problematic and how you should approach significance testing for an SEM model instead. This is the example I'll be using in this tutorial. It's a very simple structural equation model with three latent constructs: industrialization 1960, democratization 1960 and democratization 1965. And let's say I'm primarily interested in this direct effect from industrialization 1960 to democratization 1965. How should I test this? This would be the standard output using all default options. Here the estimate, the test statistic and the p-value. The default method for assigning a metric to a latent variable in most SEM programs is fixing the first loading for each factor to 1. And this default method resulted in the numbers I showed you. But that's not the only way to do it. Instead, you could set a different loading to 1 for each factor, either manually or by just rearranging the order of your items. Because after all, the items are created equal. There is not one natural first item in a factor. Or instead, you could set the factor variances to 1 and let all loadings be estimated freely. And in theory, there are many more additional options. Here you can see the results for those three options I showed you, the different path coefficients. And it makes sense that they are different because each identification method assigns a different metric to the latent variables. The standardized effect is the same for all three, because there the metric is not relevant anymore. But the problematic part is this here, the test statistic and the p-value. You can see that for different identification methods, we get different test statistics and therefore different p-values. And in this example, setting the factor variances to 1 results in a p-value that is nearly twice as high as the other two options. In this example, it's still significant, but it's easy to imagine a scenario where, depending on the identification method, for one identification method, the path you are interested in is significant, whereas for another identification method, it's not significant. So you could, by trying out different identification methods, manipulate the result of your hypothesis tests. And that's not good. There's a second problem, and that's the standardized effect, the beta. For all identification methods, we get the same standardized effect, the same beta. But if you want to report this beta, which p-value do you want to report? Because you have, for the same standardized effect, different p-values. Which one is correct? Well, the simple answer is none of them. Because all those p-values are only p-values for the unstandardized effect, not for the standardized effect. If you're used to regressions, then this is a new problem for you. Because in a regression analysis, you don't have this. There, the p-value applies to the unstandardized regression weight b and to the standardized regression weight beta the same. Here it's not the case. Those p-values only apply to the unstandardized path coefficients. If you want to report standardized path coefficients, there are some SEM programs that give you an additional column with p-values for the standardized effect. But if you don't have those, you're not allowed to use those p-values for the unstandardized effects together with the standardized effect. What is the same for all identification methods is the model chi-square. So the overall model fit does not depend on the identification method. And that's a fact we will be using later on. So what's the alternative to this highly problematic use of z-values for the significance test of path coefficients in an SEM? It's using the likelihood ratio test or the chi-square difference test. There we compare two models. First, we estimate our unconstrained model, as we have done earlier. And it doesn't matter which of those different identification methods we use there, because as we have seen, the chi-square value is the same. Then we test a second model, where one path is constrained to 0, the path we want to test for our hypothesis test. And then we run a likelihood ratio test or chi-square difference test between both models, in order to see whether the model with this path constrained to 0 fits significantly worse than the model without this constraint. And if this likelihood ratio test is significant, then we know that this path is not equal to 0, so we have shown the significance of this path. This is our model. We run this. Since the identification method doesn't matter, we can use the default option of letting the program fix the first loading for each factor to 1. And as a second model, we estimate a model where the effect we're interested in this case, the red arrow, is constrained to 0. And then we compare those two models. Here are the results. For the same 3 identification methods I used earlier. And here we can see the chi-square difference between those two models is the same, regardless of identification method. So you can't manipulate this by changing the identification method. And the p-value is the same. And since this p-value is the same, this p-value also applies to the standardized effect. This p-value you can report with a beta. There are some limitations to this approach. First, of course, it takes time. If you have many tested parameters, you have for each parameter to compare two models. One unconstrained model with one model where this specific parameter is constrained to 0. A second limitation, you could run into empirical under-identification, and in theory you could have a problem with boundary cases if you wanted to test the significance of a variance in your model, because a variance can only go into one direction. But in practice that shouldn't be a problem because you almost never have a hypothesis about a variance in your SEM model. You're interested in path coefficients and maybe correlations, but normally not in variances. So that shouldn't be a big issue for you. If you want to use this approach, the source you can quote is Gonzalez and Griffin 2001, Testing Parameters in Structural Equation Modeling. And there they make quite convincingly the case that you should use likelihood ratio tests instead of the z-test, or in AMOS critical ratio, or whatever it's called in your SEM program. That's it. Thanks for watching and see you in the next video.